Hello, my name is Islam Al-Deeb and I am a PhD student at the University of Oulu. Today I'm going to talk about our letter Multi-UEV Pulse Learning for Age and Power Optimization in IoT with UEV Battery Recharge. This letter paper was recently published in IEEE Transactions on Vehicular Technology. First, I'm going to introduce our system model where we have a grid world and the base station in the middle of this grid world. We have multiple UEVs flying over a massive deployment of IoT devices, and these UEVs are serving multiple devices at a time and relay the received information to the base station in the middle of the grid world. In addition, a UEV with a very low battery level should go to the corners of the grid world where there are battery rechargers or battery depots in order to recharge. So we need to cluster the devices. In addition, we need to optimize the optimum trajectory for each UEV in order to move. And we need to find the best scheduling policy for each UEV. And the goal is to jointly minimize the age of information and the transmission power. In the clustering step, we use the k-means to cluster the devices according to their positions. In addition, we formulate this minimization problem as MDP, Markov decision process, where we have the agent as multiple UEVs, the state space are the coordinates of the UEVs, the age of information of the devices, and the battery level of the UEVs. The action space is the movement direction of the UEVs and the scheduling policy of each UEV. The reward function is formulated with respect to the weighted sum of the age of information and the average transmission power. This average transmission power is multiplied with a certain parameter called the power parameter or lambda. This problem can be solved using the Q-learning iteratively. However, in large action and state space, it becomes very complex to solve this using traditional Q-learning, and we need function approximators to solve such complex networks. So we use deep Q networks where we use neural networks as our function approximators. So we compare the proposed deep reinforcement learning model to two models, the greedy algorithm, where its goal is to minimize the age of information without taking into consideration the transmission power, and the nearest neighbor, which minimizes the transmission power without taking into consideration the age of information. We run our simulation using 100 devices and 2 UEVs, and our power factor power parameter is equal to 25 in the reward function. And as we can see, the deep reinforcement learning move towards the areas with large number of devices. The greedy algorithm, the UEVs are moving randomly, and because it doesn't take into consideration the transmission power, the nearest neighbor barely move because it needs to minimize the transmission power only, and it serves only the nearby devices. Here we show the accumulative reward with different number of power factor, and as we can see, the accumulative reward is increasing, which confirms the learning of our deep reinforcement learning model. In addition, the ergodic age and the transmission power are shown in figure B and C. We can see that as we increase the lambda or the power parameter, we have higher age, but we have lower transmission power. And both cases outperforms the random walk algorithm. Here we have the achievable region of our proposed algorithm using 2 UEVs, 50 devices and 5 clusters. 2 UEVs, 70 devices, 7 clusters, 2 UEVs, 100 devices, 10 clusters, 1 UEV, 100 devices and 10 clusters. as compared to the greedy algorithm nearest neighbor and random walk. As we can see, as we increase the number of UAVs and decrease the number of devices, increase the number of clusters, show the best performance and the lowest jointly age and the transmission power, and all of the proposed learned scheme outperforms the traditional greedy algorithm nearest neighbor and random walk. Thank you for listening, and if you have any question, don't hesitate to contact me to my email.